We are the Aerial Robotics Club at NC State. Our current UAS, named Aquila, is a fixed-wing aircraft with an 8-foot wingspan. The aircraft has a cruising speed of 54 knots, a maximum takeoff weight of 48 pounds, and a total flight endurance of 50 minutes. It's powered by a 30cc 2-stroke gasoline engine. Aquila is designed and modeled in SolidWorks. Parts are manufactured based on these models and then thoroughly inspected before flight. Aquila's airframe is constructed from a variety of materials, including plywood, carbon fiber, fiberglass, and aluminum. Aquila's modular design allows payload modules to be rapidly tested and then improved upon. Argos is our rover that will drop from Aquila, land, and proceed to drive to a GPS location. Argos drops via linear actuators, deploying a steerable parafoil to help guide it closer to the designated landing zone, increasing target accuracy. Optionally, a circular parachute can be used in conjunction with a software program to determine a good drop point. Image capture is accomplished by the onboard flight computer, an Intel NUC running Linux. All capture, location, and gimbal functionality are implemented through ROS, or Robotic Operating System, to efficiently convey data and commands across components. Images are downlinked to the ground over a 5.8 GHz Wi-Fi connection between radios on board the plane and on our auto-tracking ground station. ArduPilot communicates with our ground station running Mission Planner using a 900 MHz radio, allowing us to receive real-time flight telemetry from the aircraft. In the event that the aircraft deviates from the desired flight path, manual control can be taken over by the safety pilot. We will be attempting the following mission tasks: a fully autonomous flight with a very high confidence in success, obstacle avoidance with moderately high confidence in success, object detection, classification, and localization with high confidence in success, mapping with moderately high confidence in success, and airdrop with a very high confidence in success. This year, we have had a total of 2.5 hours of manual flight, plus 1.5 hours of autonomous flight. Our average waypoint accuracy is 95%, with a 10-meter radius. Stability parameters are tuned using the ArduPilot Auto-Tune mode. All other parameters, including those required for autonomous takeoffs and landings, are tuned manually in response to the performance of each flight. From our imaging downlink software, the best transfer rate is 3.33 megabytes a second. At a cruising height of about 300 meters and a frame rate of 1 image per second, we get an image overlap of 20%, a map with a 16:9 aspect ratio, and a target resolution of approximately 80 by 80 pixels. A dataset of 625 images is used to train a convolutional neural network to detect targets, resulting in a success rate of 94%. Argos, our unmanned ground vehicle, has had 15 successful drops with the steerable parafoil, and 20 successful drops with the circular parachute. Each critical component has been tested individually and in combination with each other. This ensures full mission success. Here is our expected performance. Autonomous flight. 91%. Obstacle avoidance, 84%. Object detection, 80%. Imagery mapping, 82%. And airdrop success, 92%. ARC is very excited to return to the Student Unmanned Aerial Systems competition for summer of 2022. Thanks for watching, and we'll see you on the flight line.